In this video, we'll see how to calculate arc length. Also, we'll talk about a formula that we can set up to evaluate the surface area of a revolution. You'll also see both the formulas we'll come up with are basically based on the same ideas that we've been using to find the area of a region or volume of a solid of a revolution, and so on. Okay, let's say I have a function f of x defined interval. So question here is to consider smooth arc, which is graph of f of x from A to B. So length of this piece of smooth arc. It's not straight because there's no available formula to direct apply to find the length. Then what we do is what we always do. We slice the interval A to B into infinitely many sections. Accordingly, the arc is cut into infinitely many pieces. Now, if we pick up, for example, this section over interval dx as a representative, suppose the arc length of this short section is ds. Enlarge it, put it here. Let's see what we can do to try to have some idea how to figure out the length. Okay, if that's ds, then the bottom be dx. Well, say the height, call it dy. All right. Now, notice in the drawing, ds is not a straight line, but when dx is very, very small, it's always small because we cut the interval A to B into infinite many sections, and the dx approaches 0, so dx is very, very small. When dx is very small, this slanted side, this curved side, can be considered as approximately straight. This way, we can use Pythagorean theory to establish this relation. Now let's do some algebra before we take square root. So pour out the x squared. Now we see ds is simply take square root. Square root of 1 plus dy dx squared dx. Take a square of this, so dx, put it back, and take a square of the sum. Well, this would be a formula for the arc length approximately. Now we do the summation, that's addition, so the total length will be the sum of all those short pieces, length of these short pieces. Just add them up. dy dx squared. Well, here again, we end up with basically a definite interval. Let's see. We can simply denote this as y prime square dx. Well, this is how we would evaluate arc length. Now notice in this formula there's y prime, so it's assumed y prime exists from a to b. The function is differentiable. Now there's sometimes there are some even basic functions that are not differentiable throughout the interval. When that happens, for example, if you have you can just say part of a circle. Here, the derivative would be infinity. You can place a vertical tangent line. What we do is this time over an interval on y-axis, c to d, we do the same thing, slicing, so on, and there's ds, and then we would create approximately a right triangle similar to this, then go through this Pythagorean theory, take a square root, so on, then we end up with a similar formula. In this interval, the integration variable is y. X is a function of y. So if you start with y equal to f of x, what you do is just solve for x. In other words, if the function somehow is not differentiable somewhere, you try to solve for x, and try to think of this as a function of y. So you can use this formula. Alright, so we have arc length formula. When you have a function of x, now if the function of x somehow is not differentiable somewhere, you can use this formula. Okay. All right. Now, well, before I show you examples, I want to point out that it's, as you can see, very simple to set up integral this version or this version. What you need to do is just differentiate and square and plug in. So it's an integral of a square root. It's exactly because it's integral of a square root. Usually, evaluation of such integral is not possible. There are only some special cases where we can evaluate. So anyway, the main idea is not how many we can do with the formula. Rather, it's the same principle we follow to try to come up with a mathematical model as a definite interval. Slice the interval and somehow focused on short section and see what to do, and end up with a definite interval. So this is considered as yet another application of definite interval. Alright, now one more thing I want to point out. Since it's a square root, so far we don't know many integration techniques to use to evaluate general square root or radical or function, integrate a radical function. So few cases we can actually evaluate. That's when the function is given just so right that this expression turns out to be, for example, a linear function of x, like ax plus b. So we can do a simple substitution to do it, to carry out the evaluation. Or this sum somehow happens to be a perfect square. Alright, so you can see if this happens to be a perfect square root of a square, well, then you're not going to have square root anymore. Hopefully, you know, we can finish up the work, you know, find the arc length. Alright, so let's see examples. First, let's see example 1. Set up and simplify the integral that gives the length of r of function x equal to 4y minus y squared. Y is between 0 and 1. Do not evaluate. Well, it's because you'll see once we set up and simplify, it's impossible to evaluate for the time being. Okay, maybe later on. Well, we'll see what it's going to turn out. Now, the function is given as a function of y, so naturally we're going to try the second version of the arc length formula here. So we'll just find the x prime square, plug in, set up, simplify. Okay, so what do we need? Well, let me actually copy down the formula here so you see better. I'm going to use the second version. With that, okay, what do we need? We need x prime. So let's find x prime here. X as a function of y. Okay, so x prime, differentiate. You have a 4, you have a 2y. We actually need a square here, so let's square out and plug in, so we don't have to do the algebra inside the interval. Okay, x prime square equals, this is a difference, so you square that, 16 minus 16y plus 4y squared. I use the square of difference formula. You can do the Fourier, 4 minus 2x times 4 minus 2y times 4 minus 2y, or you can use distributive property. No matter how you do it, it's just algebra. You should get that. Then plug in. CD, well, it's from 0 to 1, so it's a 0 to 1 square root 1 plus. Now I'm plugging square of x prime, which is 16 minus 16y plus 4y squared. So this is how we set it up. As far as the simplification is concerned, we do what we can. Alright, so two constants, 16 and y 1, can be combined to 17. Alright, so this is the integral, definite integral came up with for the length of arc of this function from 0 to 1, and for time being, we don't know how to evaluate this definite integral. That's pretty much all we can do. Now, in terms of simplification, sometimes we'll just have to pay attention to what you can do, what you cannot do. It's algebra. For example, sometimes you may end up with square root. I'm just making up, just to make a point. Say you have a 16 plus 4y squared. All right. People often, try to simplify. That's good, and just they may do things wrong, not careful. Okay. So they thought, square root. Well, that's perfect. There's 16. There's so 4, and the square root of this guy is 2y. Somehow they end up with this, and that's wrong. You cannot take a square root of each term. Okay, just to point out, right? If it was like a multiplication, yeah, you could do that. All right, the addition or subtraction, you cannot just take square root respectively. All right, people make this kind of mistakes all the time. So just want you to know, as far as the simplification is concerned, do what you can, and also make sure you don't do wrong thing. All right. Now let's see another example. This time we're supposed to find the length of arc. Function of x is between 1 and 3. Okay, so it's not just to set up the integral. We're supposed to set up and evaluate, so we find the length. Okay, so first part. Well, you notice this is a function of x, so naturally we're going to try the first version. Okay, you can also check out, see if there's anything wrong with the y prime. In other words, is the function differentiable throughout the interval? So we'll quickly check out. Okay, again, let me copy down the formula. So it's going to be 1, 2, 3, 1 plus y prime squared dx. Okay, so what's y prime? This formula. Well, differentiate the power, bring the 3 down, so it's 1 over 6 times 3x squared, and this guy is 1 over 2. Okay, copy down 1 over 2, and then there's x to differentiate. Derivative of x is 1 over x squared with a negative sign. You could move x up there as x to the negative first power, and then bring negative down, subtract the 1, you have negative 2. That's how I got the square on the body. Anyway, what do we have here? We have a 3, 6 cross out, so the 1/2 x squared minus 1 over 2x squared. This is the derivative. Now let's quickly check. This derivative is defined everywhere from 1 to 3. There's nothing wrong with that, so it's okay that we use this version. Now I got y prime. Again, I want to do the algebra needed first on the side. It's just squared out, then plug in. So what's y prime squared? Well, I'm using again the square of a difference formula. So that's the square of the first term, square of the last term, and in the middle it's 2 times the product of those two. Now when those two multiply, x squared cancel out each other, so before on the bottom, but it's 2 times, therefore it's 2 in the middle. Okay, now I'm ready to plug this in for y prime squared. Okay. Well, notice there's 1 here, so if I plug this in, negative 2 and the 1 combined. Oh wait, I think I made a mistake. it's not -2. I'm sorry. Let's see, the product of these two, right, was 4 on the bottom with the 2, so it's actually 1/2. Sorry about that. Okay, so now let's plug in. So, well, again, there's a 1, there's a -1/2, so together will be +1/2. Therefore, we have +1/2 plus 1/4x to the 4th power plus 1/4x to the 4th power dx. Okay, well, we're supposed to find our arc length. That means we are supposed to actually evaluate this integral. This looks scary, but as I pointed out, yeah, any integral we're supposed to finish up, but evaluate, it must be very special. Either the radicand here turns out to be first order, or the radicand actually is a perfect square. Now, I'm pretty sure this thing, all those 3 terms combined, is a perfect square. Question is, how do we rewrite this as this perfect square? Well, usually it works out this way. Okay, what you do is to rearrange those terms in descending order. Start with the highest order term. This case is the 4th power, so let me copy down the 4th power. Now, next, highest order, let's see, between half and this term, this is the negative power, this is 0th power, so this is a higher order. I'm going to copy down 1/2. Then finally, so this is to rearrange terms in descending order. Always works out this way, okay? Then mechanically, we take a square root of this term, that's 1/2 x squared. We take a square root of this term, here we put a plus because it's a plus. If it's a minus, we would put minus. And this is how we usually come with perfect square, how we usually rewrite those 3 terms in descending order first as a perfect square. You can check, you can square this out, see if you get all those 3 things. You will. Alright, now the rest is some simple definite integral. Square root of square, they cancel each other. Now you see there's no more radical. As a matter of fact, this is indeed a rather simple integral. This is the power. Let's first rewrite this as a power, so we'll find the antiderivative at the same time. So antiderivative will be 1/2 times 1/3 x to the 3rd power, and here it's power, so 1/-2 plus 1 x raised to -2 plus 1, which is -1. It's antiderivative. Simplify, it's 1/6 x to the 6th power. What's this? -2 plus 1 is -1, so it's minus 1/2x. I think that's correct. 3, 1. So to finish up, plug in upper limit 3 for x. Plug in lower limit of 1 for x, 1/6 times 1 minus 1/2 times 1. Okay, with the calculator, then you'll be able to simplify to get a number which would be the length of this smooth arc of the function from 1 to 3. Alright, so as far as arc length is concerned, these are kind of problems we are supposed to do. The first kind, we just set it up and try to simplify. Okay. Second kind, we set it up and simplify and try to come up with the final answer, arc length. The ones we can do like this, remember, it's always when you plug this thing in, either the radicand is a simple first order function like a 5x plus 3, then you just do a simple substitution to evaluate the definite integral, or some rather complicated expression. In that case, most likely it's a perfect square. So what you do is to rearrange the terms in descending order, and take a square root of the first term, take a square root of the last term, put a plus or minus depending on the sign here. If it's plus, you put a plus. If it's a minus, you put a minus. And then always you can check. You can actually square out, see if you can get those guys back. If you get them back exactly same original terms, it means the perfect square is correct. Okay, it's simple to check. Once you end up with a perfect square, square root of the square cancel each other, so evaluation usually is pretty simple. Alright, now this section is titled arc length and the surface area of a revolution. So in addition to arc length, there's a area of surface of a revolution we want to talk about. Now let's say there's a function with a graph showing over interval a to b. Suppose we revolve this arc, this curve, around a line, maybe x-axis. Okay. The revolution of the curve would look like this. Now this is like how we revolve a region before. Before we revolve a region, so revolution is solid. This time revolution of a curve is only a surface, like the surface of the revolution of solid we had before. All right. So it's a hollow. Okay. So the question is, how would we set up a mathematical formula to calculate the surface area here, lateral surface? There's no end. Well, we would slice the region again. Accordingly, the curve is sliced. So what we do is to pick up a section over interval dx. And consider the revolution of this little short arc length. The revolution of the little short section is like first term, pretty much like this if you put it on table. Okay, so question is, how are you going to find the surface area of this first term? Well, our assumption is dx is very short, very small. Therefore, the ds can be considered as a flat. So it's like we almost have wingspan. Okay. The question is, what's the area of this wingspan? Well, it's like a lateral surface of a cylinder. The formula we have is a 2 pi r times ds. ds is like the width of the wingspan. R is radius of the cross-sectional circle, just like how we evaluate cylindrical shell. Remember, volume of cylindrical shell. So this wingspan, if you put it on table and make a cut, there's no width. So this is ds. The circumference is 2 pi r. Therefore, the length of this cut wingspan is 2 pi r. So the area, thin piece of paper, is 2 pi r, which is length times the height. Now, the total area, of course, will be the sum from A to B, the sum of all those areas. And ds is the arc length here that we calculated before. So it will be the same formula. If we think that it's a function of x, it will be 1 plus y prime squared dx. Now, what's r? Well, depends. This case, r will be this distance. So depending on the function, depending on the line around which the curve is rotating, so we would, each case try to find the expression for the radius, okay, as a vertical distance, or could be horizontal distance if the graph is rotating around a vertical line. In that case, we may have a dy2, just like before. So either case, we would end up with a definite integral. All right. So this could be x prime. This could be dy. The r could be different, from problem to problem. The idea is, okay, we see the mathematical formula we set up for the surface area of such revolution is definite integral. Now this definite integral is more complicated than the definite integral for arc length, because we may have stuff here which can be bad. All right, even without that arc length case, most of the time it's impossible for the time being for us to evaluate. Not with the R. 2 and pi don't present any problem. We can always move out. It's the R here. Okay, it's at least x or y there. Could be x minus number, x plus number, could be y. So that's going to make this a whole lot more complicated. For this reason, for the surface area of a revolution, we just want to see how to come up with the formula. We don't worry about the evaluation at all, because most of the time it's impossible, and also because our focus is on the idea based on which we arrive at another definite integral. So this is considered as one more application of definite integral. Alright, so in this section we don't do any problem related to surface area of a revolution. The problems we are responsible are similar to the examples I showed you. One, you just set up the definite integral, set up and simplify as much as you can. Definite integral for the arc length. Other kind, you set it up. Hopefully you can finish up the work finding the arc length, set up integral, and evaluate the integral. Alright.